The physics of ultrasound imaging. History of ultrasounds. In 1794, Lazzaro Spallanzani was the first to study echolocation in bats. This became the basis of how ultrasounds work. The sound waves bats produce are reflected off of objects in the environment, which then reach the bat again so the bat can avoid those objects. In 1877, brothers Pierre and Jacques Curie discovered piezoelectricity, which is how transducers produce and receive sound waves. In 1915, Paul Langevin invented a hydrophone to detect objects at the bottom of the ocean. This is referred to as the first transducer. In 1942, Carl Dusek was credited as the first to use sonography for medical diagnoses. He detected brain tumors through the human skull with ultrasound beams. In 1948, George D. Lugwing developed the A-mode ultrasound equipment to detect gallstones. Between 1949 and 1951, Douglas Howry and Joseph Holmes pioneered the B-mode ultrasound equipment. John Reed and John Wild invented a handheld B-mode device to detect breast tumors. In 1966, Don Baker, Dennis Watkins, and John Reed designed a pulse Doppler ultrasound technology. In the 1980s, Kazunori Baba developed 3D ultrasound technology. Piezoelectricity. Piezoelectricity is the process of using crystals to convert mechanical energy into electrical energy and vice versa. Piezoelectric crystals can be naturally based, made out of quartz, topaz, Rochelle salt, or man-made such as lead zirconate, titanate, barium titanate, or lithium niobate. Man-made crystals provide more voltage and longer-lasting durability than natural crystals. The piezoelectric crystal is placed between two metal plates with a completed circuit. The direct piezoelectric effect is the process of applying mechanical force to the metal plates. This mechanical pressure forces the electrical charges within the crystal out of balance and the excess positive and negative charges to appear on opposite sides of the crystal face, which are then collected by the metal plates. These charges then travel through the circuit and create a voltage. In an inverse piezoelectric effect, electrical signals are applied to the circuit. The charge then travels through the circuit to the metal plates, which then reaches the crystal. The electrical charge causes the internal crystal structure to shrink and expand. As the structures shrink and expand, energy is released in the form of sound waves. This is how ultrasound transducers produce sound waves. Transducers. Transducers are the handheld piece of an ultrasound responsible for production and detection of ultrasound waves. Inside the transducer, there is a piezoelectric crystal and completed circuit. Behind the positive metal plate, there's a damping block. The damping block absorbs ultrasound energy directed backwards and weakens stray ultrasound signals. It creates a shorter spatial pulse length, which allows for better axial resolution but higher bandwidth. In front of the piezoelectric circuit, there's a matching layer, which is the interface between the transducer and the tissue. This allows close to 100% transmission of ultrasound waves from the transducer into the tissue due to minimized reflection between transversing different mediums. The entire transducer is inside of a housing case, which consists of electrical insulation and protection of the element. It includes a plastic case, metal shield, and acoustic insulator. There are four main modes of ultrasounds. An A-mode ultrasound is a single transducer line that goes through the body and creates a series of vertical peaks. These peaks represent the beam as it encounters the boundaries of different tissues. A B-mode ultrasound uses a linear array of transducers simultaneously scanning a plane through the body. This is viewed as a two-dimensional image on the screen. The M mode is a rapid sequence of B mode scans whose images follow us in a sequence on a screen. This enables doctors to see and measure range of motion as organ boundaries that produce reflections move relative to the transducer. A Doppler mode ultrasound uses the Doppler effect in measuring and assessing whether objects are moving towards or away from the transducer and their relative velocity. How ultrasounds produce an image. Ultrasounds emit and receive sound waves through the transducer. When the transducer receives the sound waves, they are converted into electrical signals in the piezoelectric circuit. The electrical signals are then sent to the ultrasound scanner. The scanner uses the speed of the waves and the time of each echo's return to calculate the distance from the transducer to the tissue boundary. These distances are then used to create a black and white two-dimensional image on screen of tissues and organs. The physics behind an ultrasound. The key to the physics of an ultrasound is sound waves. Each wave has a speed when traveling through the body, which is determined by the stiffness and density of the tissues in the body. The equation for the speed of the wave is c equals k over p to the 1/2. The acoustic impedance is the degree of difficulty of the sound wave being transmitted through a medium. This equation is z equals p times c, p being the density and c being the speed of the wave. As the waves travel through the body, they encounter tissue boundaries. When the waves meet the tissue boundaries, some of the wave is reflected off the boundary while some is transmitted. This occurs similarly to optical reflection. When the waves are transmitted through the boundary, they experience refraction, which is the redirection of sound waves when crossing between medias. When sound waves encounter rough surfaces or heterogeneous media, scattering occurs, which is the redirection of sound waves in any direction. Most of the waves are eventually reflected back towards the transducer. However, some are lost due to absorption, which converts sound energy into heat energy in the tissues. The impacts of ultrasounds. Some advantages to ultrasounds are that they use non-ionizing sound waves, which greatly decreases the risks of ultrasounds versus X-rays, which use ionizing radiation. Another advantage is since ultrasounds are smaller in size, they are typically cheaper than an MRI or a CT, and more readily available since it doesn't cost as much to have multiple machines. However, ultrasounds are not capable of evaluating the internal structure of tissues as well as an MRI or CT could. Another disadvantage is that high frequencies of the ultrasound could potentially result in thermal heating or injury to the tissue at a microscopic level. This is the biggest concern with fetal ultrasound imaging. Overall, ultrasounds are used by a multitude of medical professionals to examine organs, large blood vessels, perform musculoskeletal scans, breast scans, and pregnancy scans. Because of their low risk, comparatively inexpensive cost, and the widespread capabilities and use, ultrasounds are a very important part of the medical field.